The movies are one of chemistry's great achievements. First, organic chemists invented celluloid film, which started it all off. Then, some years later, they came up with the organic dyes, which gave us modern colour pictures. How did chemistry get so smart? This man is credited with cracking the biggest mystery of all, the behaviour of the elements. Dmitri Mendeleev's periodic table of the elements would revolutionise chemistry.
Mendeleev was a Russian. He was born in Siberia. For all his hairy looks, he was very intelligent, hard-working and quite liberal-minded for his day. Now, Mendeleev comes along in the 1860s, when organic chemists are just starting to classify all of the different compounds of carbon and hydrogen. And he says, why not go beyond this to all of the elements? And he creates his famous periodic table.
The periodic table began simply as a list of all the elements, beginning with the lightest, hydrogen, and going on in the order of weight. Helium, lithium, beryllium, boron, and so on. But instead of being just a list, they were arranged in rows so that similar elements go under each other. For example, fluorine, chlorine, bromine and iodine are in the same column because they are chemically alike. And this is what has been done for all the columns. All of a sudden, the big picture starts to emerge. All the metals group over to the left, and all the non-metals are over on the right. Carbon sits right in the middle of the first row of 8.
In Mendeleev's day, not all of the elements were known. For example, none of the so-called noble gases had been discovered, so the right-hand column didn't exist. But it didn't matter. Everybody could see, for a start, that you could count into an element from the sides of the table, and the count gave the elements combining power, its valency. 1 into fluorine, 2 into oxygen, 3 into nitrogen, and 4 into carbon, for example. Mendeleev's table of 1869 had many gaps and inaccuracies. And why the elements lined up this way, it wasn't really known. But the table was a big thing. It showed the path to follow.
The periodic table confirmed what chemists had suspected a few years earlier, that carbon's place in the chemical lineup made it extremely versatile. As Friedrich Kekule had shown, carbon had the ability to connect its atoms into chains. This tied every atom to a neighbour either side, but with a combining power or valence of 4. Every carbon atom in a chain could still spare 2 bonds to attach side atoms. The commonest side atom was hydrogen, the simplest atom of all, offering but a single bond. Indeed, these 2 atoms alone formed a complete family of compounds, the hydrocarbons. It's a family we all know very well, because it's an intimate part of our lives. Most of the products of the oil industry, which we use as fuels and lubricants, are from the family of the hydrocarbons. Carbon's flexibility makes for a dazzling array of combinations.
Organic chemistry has literally millions of compounds, but there's a very attractive logic to it. Let me show you the most basic family of the hydrocarbons, the alkanes. Here's its simplest member. It's the gas methane. It's 1 carbon surrounded by 4 hydrogens, all single bonds. Now, let's take off this hydrogen and add another carbon, and we'll put the hydrogen back on the end. We have 2 extra bonds, so we'll add 2 more hydrogens. Here's ethane. It's also a flammable gas. Now let's build the next one. We'll take off this hydrogen, add another carbon, put the hydrogen back on the end, and include 2 more hydrogens. Now we have a chain of 3. This is propane. And you can see the simple formula for the alkanes building up. It's always the carbon number plus double the number of hydrogens plus 2 for the ends. And you can go on like this to very long chains indeed.
As the carbon chains get longer, so the substance gets denser, changing from gas to liquid, which gets thicker and thicker, until finally it becomes a solid at normal temperatures. But a straight chain is only a beginning. By the time we get to butane, there is another arrangement possible. The chain can have a branch. This is an example of a new substance being formed, not by a change in the numbers of atoms in the molecule, but solely in their arrangement. It is an isomer of butane. So what is this substance?
That's a very good question. Part of finding a path through the organic maze is in the names, but it isn't easy because a lot of these substances were known and named long before structural diagrams or the periodic table brought a general order into chemistry. Take this very simple example of the one and only isomer of butane. It's often referred to as isobutane, but this is really confusing because the iso part is not referring to isomer, which means equal parts. It's referring to equal methyl groups. As far back as 1889, chemists were saying, hold it, we need a naming system that helps, not hinders.
These are the names given to the alkanes by the International Union of Pure and Applied Chemistry, or IUPAC as they call it. The ane ending refers to the alkane group, and the different beginnings refer to the number of carbons in the main chain. This is simple enough, and they stay with this basic rule for isomers. For example, in butane's only isomer, the main chain has lost a carbon to the side branch, so it is really only 3 carbons long, which makes it a propane. The hydrocarbon branch is called a methyl group because it has a single carbon, so this is methylpropane. And the methyl group is on the second carbon on the chain, so the IUPAC name is a useful description, 2-methylpropane.
Butane can only have one other isomer, but as we lengthen the chain, there are many different isomers which become possible. Look at this. I've just drawn a pentane chain, 1, 2, 3, 4, 5, and I've attached a methyl side group here and here. Now the naming rule says find the longest chain, 1, 2, 3, 4, 5, remembering pent means 5. Pentane, that gives the N part of the name. Now we'll name the side groups. We have a methyl group here, and 2 of them makes dimethyl. And now we'll name the side groups to the carbons to which they're directly attached, starting from the closest end. Here it's the second and third carbon, so this compound is 2,3-dimethylpentane.
Suddenly, we begin to get a hint of why there are so many more organic compounds than inorganic ones, due to the amazing ability of carbon chains to act as a spine in so many different molecules. Yet these are just one family, the most basic, the alkanes. We are dealing only with the atoms of carbon and hydrogen, and all of the connecting bonds are single. So what about double bonds? Could there be another family with double bonds?
Oh yes, the party's just beginning. Up to now we've seen the alkanes are saturated. That means the bonds are single, and all the carbons are attached to the maximum number of hydrogens possible. But it doesn't have to be like that.
If carbon can join to carbon with one of its 4 bonds, then why not 2? The family of hydrocarbons which have a carbon-to-carbon double bond, or maybe more than one in the molecule, is the alkenes. Alkanes are saturated, but alkenes are not. Because the carbons are hogging 2 bonds now, there's fewer available for other atoms. This is the simplest member, the gas ethene. The formula for alkenes is thus only the number of carbons plus double this number for hydrogens.
Life starts to get really interesting with the unsaturated groups. Take ethene gas for a minute. It burns much like methane because the alkenes look and behave very similar to the alkanes, except that their double bond makes them more reactive and therefore more useful. Burning them could be considered a waste because you can take that double bond, open it and make it grab another carbon. Of course, that would convert the alkene into an alkane. Now you may say, so what? Well, this is so what. This is polythene. As the carbons join up, they make huge long chains, greater than 100,000 carbons in length sometimes. From ethene gas, we can make polythene plastic. That double bond is really useful.
And from double to triple. Now the family name is alkyne, and following the naming rules, the simplest member is the gas ethine, which is often used in welding. It's commonly called acetylene gas, which again illustrates the naming problem. It also illustrates the fact that triple bonds release even more energy than single or double. Ethine burns with a very hot flame. 3 families of hydrocarbon: alkanes, alkenes and alkynes, with characteristics explained neatly by chemical theory. It seemed that hydrocarbons were understood at last.
The nice thing about science is that just when we think we know it all, nature pops up with something that's a new challenge. Take benzene. Here's a hydrocarbon that defied all the rules. It has a formula C6H6. Now you try making a carbon chain out of that. Single bonds, double, triple, it won't add up. It was Kekule who yet again came up with an answer and created another family of hydrocarbons. He said he dreamed of whirling atoms, which turned into snakes, and the snakes coiled around and bit their own tails, and he woke up realising that the carbon chain had formed into a ring.
Benzene was a 6-carbon ring containing 3 double-bonded carbons. But which 3? And why was benzene much less reactive, much harder to break up than any others of the double-bonded family, the alkenes? Even though many carbon chains would be shown to exist as rings. For example, chemists would discover cycloversions of alkanes, alkenes and alkynes, but the benzene ring of 6 carbons and 6 hydrogens would remain in a class of its own, stubbornly different. Chemists guessed that the reason had something to do with the way you couldn't pin those double bonds down. They seemed to flit around the ring as they wished, and somehow they gave this ring a special stability. Benzene is unique. It stands alone as the family of aromatics. But an explanation would have to wait. It would have to wait for the chemical discoveries of a new century.